So in our last video, we looked at the general trends that we see across the periodic table. Now let's take this opportunity to dive into these a little bit further and look at those exceptions, all right? Because as we know, the only rule in chemistry is there are no rules. So let's start with ionization energy. The general trend that we notice as we move across the periodic table is as I move across from hydrogen to helium, from lithium to neon, from sodium to argon, which is as I move across the periodic table here, yes, from hydrogen to helium, lithium to neon, etc. We do see an overall increase in the first ionization energy. And again, this is just the first ionization energy. What happens as we move down a group in the periodic table? So as I move down a group in the periodic table, I see an overall decrease in ionization energy. But let's look at lithium, beryllium, and then we go down boron. Boron has a lower ionization energy, first ionization energy, than beryllium. Then we see it start climbing again, and oxygen drops back down, and then we see it starting to climb again. So what accounts for these changes in ionization energy? And these changes can best be described if we are to draw our orbital notation. So let's draw the orbital notation for lithium. And let's draw the orbital notation for beryllium. So when we look at the orbital notation, we notice that lithium has a 2s with an unpaired electron, and beryllium has a 2s which is paired. Now, if we were to draw the orbital notation for boron, what do we notice? Why does boron drop down? Boron drops down because it has one electron in the p group. All right, so it has one electron in the p group. So boron is pretty willing to get rid of this one electron in order to go ahead and get it to be more stable where it has a 2s that is completely filled. Because there's only one electron in the p, this makes it a lot more unstable. Well, I shouldn't say a lot more unstable. We should be careful with the words a lot and much, but it does make it more unstable. Therefore, it's very willing to give away that electron, all right? More willing to give away that electron, causing its ionization energy level to drop down, all right? Let's look at oxygen. Why does oxygen drop down compared to our nitrogen and our fluorine? So if we were to draw the diagram for oxygen, notice that oxygen has one electron that is paired, and with this electron, so that we've got one pair of electrons and two unpaired electrons. What do we notice about nitrogen? Nitrogen has no paired electrons, but its p level is half filled. So if you'll think back when we were learning how to draw orbital diagrams, and we were talking about it being half filled, and we looked at the D group and we said that we talked about electron shifts and stuff like that. We're not going to see electron shifts or anything here, but the concept of a half-filled orbital is still there. A half-filled orbital is stable-ish. All right, so nitrogen actually has a higher ionization energy than oxygen, because oxygen can simply lose one electron, and by losing that one electron become half filled like nitrogen, making it more stable. So oxygen's actually a little bit more willing to lose an electron than nitrogen. All right, let's look at our ionic radius. Let's talk about these trends. What do we notice for our ionic radius? Our ionic radius decreases a bit and then it jumps up and it decreases again. Same thing as I go across from sodium to silicon, it decreases, and then at phosphorus, it jumps up again. So as I go from sodium to silicon, it decreases, and then at phosphorus, I jump up again and then start to decrease again. So what is happening here? And let's look, in order to describe that, we're just going to simply look again at our electron configurations. So if I was to draw the electron configuration for a lithium neutral atom of lithium, it is 1s2, 2s1. And if I was to draw it for a lithium ion loses one electron to become 1s2. So what are we doing here? When lithium forms an ion, it loses an energy level altogether. Let's look at fluorine. The electron configuration for fluorine in its natural form is 1s2, 2s2, 2p5. Now in its ion form, it is 1s2, 2s2, 2p6. So why do we jump back up here? Because fluorine, when it gains an electron, it keeps its second energy level. So by keeping its second energy level, it has two energy levels. Lithium loses an energy level. All right, so we have two energy levels for nitrogen, oxygen, and fluorine. And for our lithium, beryllium, and boron, we are losing an energy level, which accounts for an increase. Now, why do we see a decrease between oxygen and nitrogen? Oxygen and nitrogen, and even fluorine, they are all on the second energy level. They all have two energy levels. What we see here as we move across, though, we go from nitrogen to oxygen. We are adding protons. So by adding protons, we are increasing that effective nuclear charge. And an increase in that effective nuclear charge brings a stronger attraction for the electrons in each of the elements as we move across. So we increase protons, therefore we increase the effective nuclear charge, and that's going to bring the second energy level in oxygen closer to the nucleus than it was in nitrogen, and even closer in fluorine, because fluorine has even more electrons. I'm sorry, even more protons. Fluorine has even more protons than nitrogen. Yes, fluorine has 9 protons and nitrogen only has 7.